Okay, Bismillah Rahman Rahim. So today is lecture number 11 and we will continue with the chapter Unsteady Flow Problems. So in the previous lecture, we studied unsteady flow problems where the flow characteristics, they are changing with respect to time in a fluid flow. And then there are two main types of unsteady flow problems that we are going to cover in this chapter. So the first one was the unsteady flow problems where the changes take place slowly. For example, the rise and fall of water level in a tank. So essentially, we studied about those types of problems in the previous lecture. The second main type of problem that we are going to discuss in today's lecture, where the changes take place rapidly. And I give you example last time that when we suddenly open or close a valve, so the changes that will take place rapidly. So today we are going to cover this second type of unsteady flow problem. So before we start with that, so we need to study a topic that is known as velocity or celerity of pressure waves. So this is to calculate that with what velocity the pressure wave that setups in any liquid, any medium, and with what velocity it will travel. When we suddenly close the valves, what happens is that the momentum of the moving fluid is destroyed. Means you suddenly bring it to rest. So when you suddenly bring to rest, energy cannot be destroyed, neither created, so it can be converted from one form to another form. So what will happen that when kinetic energy is brought to rest, it will result in increase in pressure. So this increase in pressure, it will travel up the pipe from the valve which is just closed in the form of pressure waves. So we are interested to know that with what velocity these pressure waves will travel. And then later on we study what is the effect of this. So this is what we are looking into in this topic. So to calculate the equation for velocity or celerity of pressure waves, we consider an elastic fluid. Now elastic fluid, we consider the fluid as compressible. So far in most of the problems we treated the fluid as incompressible. Now in these topics we will treat the fluids as compressible, elastic fluid in a rigid pipe. So when we use the term rigid, it means that the body is non-deformable. Clear? So that we call it as rigid body. You studied mechanics of solids. So we consider the pipe to be rigid. There is no change in shape and size of the pipe. Only the fluid is treated as elastic. So the pipe has a cross-sectional area A. Now what we do is that suppose a piston at one end is suddenly moved with a velocity v for time dt. So now on one side we have this piston, this section 2, this is fixed. Clear? This is fixed. What we do is that we move the piston and there is a elastic fluid here in this piston. So when we move this piston, so we move this piston with a velocity v. So in time dt, the distance that it cover will be v times dt. From where it comes from s is equal to vt. We have this s is equal to vt. So we move the piston with a velocity v, the distance it covers in dt, that is equal to v times dt. Now because we compress the fluid, you see here the fluid is not moving beyond this section 2, we are compressing the fluid. So what will happen that this will produce an increase in pressure. This will produce an increase in pressure which will travel through the fluid with a velocity c. So this we denote with c. What will happen is that it says that when you push this fluid by application of this piston here, so this will produce increase in pressure. The pressure will increase, clear? So this pressure, it will travel in the form of a wave from this section 1 to section 2 in the fluid. This increase in pressure, it will travel through the fluid in the form of a wave with a velocity c. So it means that in time dt, it cover a distance c dt. So this pressure wave which is generated and it travels with a velocity c, we want to calculate equation for that or develop equation for that so that we can calculate that with what velocity the pressure wave will travel. And then later on in the topic you will see that what is the importance of this, why we are interested to calculate the velocity or celerity of pressure waves. Because when it travels, this is a pressure effect, so it increases the pressure at that point in the flow where it passes. So that's why we are interested to calculate that what is the velocity of the pressure wave. Now in this case you see that the piston is moved. You see that the piston is moved in this direction. So it has displaced a mass of fluid, clear? Since we have compressed the fluid, so we have displaced a mass of fluid. So how much mass of fluid is displaced? That we can calculate mass displaced, that is equal to rho into volume. So you already studied density, mass density. So this mass density, this is equal to mass divided by volume. So we denote by this notation to differentiate from the velocity. So now the mass which is displaced as we move this piston, so that is equal to density into volume. So density will be rho, and what is the volume that is displaced? It is V into dt multiplied by the cross-sectional area. That is the volume which is displaced. So this is the density. The density comes here, the mass density of the fluid, and this volume here, this is equal to product of area into velocity into the short time dt. So in the short time dt, this is the volume which is displaced, clear? So the mass displaced will be density into this volume, clear? Because from here you can see that area is square meter per second and then second. So we are left with the units of volume. Now this increase in pressure dp, as we already said that this will produce increase in pressure, clear? So this increase in pressure dp will increase the density of the fluid between section 1 and 2 by d rho. Because we are compressing the fluid, so the particles, they will come closer. So when the particles come closer, the density will increase because the mass per unit volume will increase. So the increase in pressure dp will increase density of the fluid between the two sections by d rho. Let's say the increase in density is d rho. So now we have the mass displaced and now the density has increased, so it means there is a gain in mass. So the mass gained between this section 1 and 2, that will be equal to again rho into volume. So we have d rho because this is the mass gained. We talk about the mass gained. So the mass displaced there, and this is the mass gained by the fluid between section 1 and 2. So that's why this is d rho. The change in density that will occur as a result of increase in pressure. So d rho into this volume, AC into dt. Area is the cross-sectional area of the piston. and c dt is the velocity with which the pressure wave travels. So this will be the mass gained by the fluid between section 1 and 2. Now we can apply the law of conservation of mass. And what law of conservation of mass says? That the total mass is conserved. Clear? The total mass is conserved. So it means that mass displaced is equal to mass gained. So essentially we can write down these equations here. Now we compare these two from law of conservation of mass, that mass displaced is equal to mass gained. Now you can see here that the area which is present on here, both sides cancel out. Similarly, this dt cancel out with this dt. And when we simplify, so c is equal to rho v divided by d rho. So this is now the expression for velocity of the pressure wave that will set up and it will travel through the fluid. So the pressure wave which will travel through the fluid with this velocity, which we denote by c. Now you can see that in here density, this is the fluid property, velocity is with which the piston was moved, clear, and d rho is the change in the density, clear, as we compress this fluid between section 1 and 2. Now next what we consider, because you see in this equation it's not very easy to calculate this c, because rho v, okay, we can normally calculate with what speed you move the piston, the density of the fluid can be known, but how to calculate the change in density or increase in density in this case? So that's why we should look for an equation that we can conveniently use to calculate this velocity of the pressure wave. So next what we do is that we apply the impulse momentum equation. As I said before, that in fluid mechanics, three fundamental equations we use very frequently to solve the problems. The first one is the continuity equation, clear. Second one is the Bernoulli equation. So you see that we solve these fluid mechanics problem using these equations extensively. And whenever we are interested to calculate forces, then we have to use this impulse momentum equation. So this is nothing but it is just application of Newton's second law. So what we say is that from the Newton's second law, we say that F is equal to ma. This is Newton's second law. Now this acceleration, this can be written as rate of change of velocity. So we can write down here dv by dt. And as you studied at college level, maybe in physics, this we can write down here F into dt. So this is equal to m into dv. So you already studied that the force multiplied by the short interval time dt, this is known as impulse. This is known as impulse. And we already know that product of mass and velocity, this is known as momentum. This is called momentum. So that's why we have this impulse momentum equation. So I can write down F into dt is equal to m into dv, where dv is the change in the velocity. So now we have to consider the forces. So let's say I consider the fluid between these two sections here. So the different forces that is acting on here, the pressure forces. So this will be equal to P into A, because the cross-sectional area of the piston is A. And then in here, what we can write down is that P plus dP, because there is increase in pressure, so we have this P plus dP into area A. And as this piston is moved, so the fluid with this movement of the piston, what happens is that the fluid which was initially at rest, now it moves with a velocity of capital V between two sections. When you consider any two section, so the fluid, since the piston is moved with a velocity V, so the fluid, it will attain a velocity V. We are pushing it with that same velocity, the fluid, clear? So that's why the velocity will be V from initial velocity 0. Remember, this C is the velocity of a pressure wave, clear? So now we can consider this here. So since the forces are not in the same direction, so we can calculate F into dt, summation of the forces into dt. Then we have the mass. So the mass we already discussed, rho AC into dt, clear? And the change in velocity is your final velocity minus initial velocity. So we have V minus 0. This is V minus 0 is the change in the velocity dV. So now if you simplify this, we get C is equal to dP by rho V. So this equation here is change in pressure divided by rho V. This is dP, change in pressure, clear? Now you see that we have C is equal to dP by rho V, and also we have C is equal to rho V by d rho. So we can compare the two equations. So now multiplying equation 1 with equation 2, when we multiply the two equations, clear? So in this case, what we get? C into C and rho V by d rho into dP by rho V. So now you can see that rho V and rho V cancel out, and we are left with C square is equal to dP by d rho. C square is equal to dP by d rho. Change in pressure divided by the change in density. Now we consider the fluid to be elastic. As earlier we stated here that consider the fluid to be elastic. We are considering elastic fluid, so that's why we have to bring the elasticity into the analysis. The pipe is rigid. Pipe is not going to change in say shape and size, but we only consider the fluid to be elastic. So now we consider that, and you already studied in fluid mechanics 1 that when we consider the fluid to be elastic, so we consider volume modulus of elasticity. That is a parameter which gives us idea about the compressibility of the fluid. And how it is defined? It is denoted by EV, volume modulus of elasticity, or bulk modulus, is equal to change in pressure divided by the volumetric strain. dV, d nu by nu. This is actually the specific volume. So remember, nu we use to denote kinematic viscosity, but also we use nu to denote the specific volume. So this is volumetric strain, change in volume divided by original volume. So when you compress the fluid, the volume is going to decrease. That's why the negative sign is there to make it positive. It will make the answer positive. So that's why we put this negative sign here. Now in this case, this change in pressure divided by the volumetric strain, this we define as the volume modulus of elasticity. So now we already know that density and specific volume, they are inversely related to each other. What is density? Density is your mass per unit volume. And what is specific volume? It is volume per unit mass. So they are reciprocal of each other. So we can write down rho into nu is equal to 1 from here. If you bring this here, so it will be rho into nu equal to 1, or 1 is a constant. So this product is a constant. Clear? Now if I take derivative of this, so what we write down here, we have rho into V. This is equal to 1. So if you take derivative of this, I will apply the product rule. So how we apply the product rule? You say that first function into derivative of second function plus second function into derivative of first function. So we write down first function into derivative of second function plus second function into derivative of first function, and derivative of a constant is 0. So this is what we can write down here. So now if you rearrange this, this is what we get. Clear? And from here, this minus d nu by nu, this is equal to d rho by rho. Now from here, what we get? Minus d nu by nu is equal to d rho by rho. So now it means that in here I can replace this now in the volume modulus of elasticity by what? I can replace this by d rho by rho. So now this EV, this is equal to dP divided by d rho by rho. So this can be rearranged like this here, and now we get d rho by dP by d rho. This is the pressure, change in pressure. This is the change in density. So dP by d rho, this is equal to EV by rho. Now you see here that we have dP by d rho equal to EV by rho, and in equation number 3 we have dP by d rho equal to c square. So now we can compare equation 3 with equation 4. We can compare equation 3 with equation 4. So we get c square is equal to EV by rho. And from here, c is equal to square root of EV by rho, also equal to g by gamma EV. Because you already know that this gamma, this is equal to rho into g. So now this is the equation that can help us to calculate the velocity or celerity of a pressure wave, also known as the sonic velocity. Now you can see here that the velocity with which the pressure wave will travel in a fluid, that depends on the properties of that fluid. You can see here the bulk modulus of that fluid. Similarly, the density of that fluid. So that's why we can say that this velocity or celerity of pressure wave, it is not constant, but it will depend on the fluid through which the pressure wave will travel. So these are now the fluid properties. For any given temperature, you can read these properties from tables, and then we can calculate that with what velocity the pressure wave will travel in that medium. So this is the equation which is directly given in your textbook chapter. I derived this equation for you so that you understand from where this equation comes. Clear? Now in this equation, we consider only the fluid to be elastic. Clear? This equation, which give us the velocity of a pressure wave that will travel through the fluid, this is also known as celerity. Why it is called celerity? Because this is the velocity of a pressure wave, and you already studied about the nature of the waves in school, colleges. Clear? In the physics course. So in that case, this velocity, this is not actually the velocity of a physical matter. This is the velocity of a wave. This is not the velocity of a physical matter. So that's why it is given the name celerity. That's why it is known as celerity. We can call it velocity or celerity of pressure waves. Now, in unsteady phenomena with rapid changes taking place frequently involve the transmission of pressure waves. Clear? This is now we are coming to what is given in your textbook chapter. That when we have rapid changes that take place, for example, suddenly opening or closing of a valve, so then in that case we have unsteady flow phenomena. Then in that case, frequently these phenomena involve transmission of pressure waves or surges. So the velocity or celerity of the pressure wave is given by this equation that I just derived for you. This is now given in your textbook chapter. So I derived this equation for you, so you understand that from where this equation comes. Now in this case, EV is the bulk modulus or modulus of elasticity of the medium. For our typical value of EV 300,000 psi, or this value in kilonewton per square meter, thus the velocity or celerity of a pressure wave in water is about 4,720 foot per second. It means that in water, if you generate a pressure wave, so it will travel with a velocity of 4,720 foot per second, or we can say 1440 meter per second. Why it will depend on the temperature? Because you see that density and this bulk modulus, it can vary with temperature. So for any given temperature that you consider the values, the typical value, so this is around 4,720 foot per second or 1440 meter per second. This is for water. If you have another liquid, this will change. As I said, that this will depend on here the fluid properties. But for water, if a pressure wave setup, for example, you have a pipe and you suddenly close the valve, so this will result in set up a pressure wave. So this pressure wave, it will travel with a velocity of 4,720 foot per second. But remember, this will be the velocity when the pipe is rigid. When the pipe is rigid, only the fluid is elastic. But if we have elastic pipe, for example, we have plastic pipe that can be elastic, so then in that case, for water in an elastic pipe, this velocity is reduced. Why? Because the pressure will be taken or resisted by the walls of the pipe also, because the pipe will then expand. So it means some of the effect is taken by the pipe. So as a result of that, the pressure wave velocity will be then less than this value. So if we consider the pipe to be elastic, then we have to modify this equation. Then you cannot use this equation to calculate the velocity or celerity of pressure waves. So the velocity is reduced due to the stretching of the pipe walls. So EV is replaced by joint or combined modulus of elasticity. Whenever you see the term with a subscript J, it means that it is the joint or the combined modulus of elasticity or celerity of pressure wave. So when we consider the joint means for the elastic fluid and the elastic pipe. So that's why it is the joint or combined modulus of elasticity. Then this C, it will then change to Cj, the joint celerity of pressure wave. So then in that case, this Ej is then given by Ev divided by 1 plus d by t, Ev by E, where d and t are the diameter and wall thickness of the pipe respectively, and E is the modulus of elasticity of the pipe material. So then this Ev we have to replace by Ej. So according to that, then the velocity of a pressure wave in an elastic fluid inside elastic pipe is then Cj. You can see here now this is the joint or combined celerity or velocity of the pressure wave. So instead of EV, now we are using EJ, and it can simplify in these various forms. So then if we treat the fluid and the pipe both as elastic, then this value formula we can use to calculate the velocity of the pressure wave. If the pipe is rigid, only the fluid is elastic, then we can use this formula to calculate the velocity of the pressure wave. So since the pipe is there, so for normal pipe dimensions, the speed Cj of a pressure wave in a water pipe usually ranges between 2000 to 4000, but it will always be less than 4720. This is what we said, because this is for the velocity of pressure wave in free water when the pipe is rigid. So in free water, the pressure wave will travel with this. When the pipe is also considered as elastic, when the pipe is treated as elastic, then in that case, the pressure wave velocity will be reduced. It can range, depending on the situation, between 2000 to 4000, but it will always be less than this value here. So now in this topic, we developed the equation for calculating the velocity or celerity of the pressure waves, because we stated that when we have unsteady flow problem where changes take place rapidly, pressure waves will set up and they will travel through the medium. So we are interested that with what velocity they will travel. And after this, I will show you that what is the effect of these pressure waves. So this is very important. I derived the equation for you, that how this equation is developed. And now we can calculate the celerity of the pressure wave for elastic fluid as well as for elastic and elastic pipe. Elastic fluid and elastic pipe both. So now for any given fluid and pipe material, we can calculate using these expressions the velocity or celerity of the pressure waves. Now we come to the important phenomena that is known as the water hammer. So this is the next important topic. This is a conceptual topic. I will explain this every aspect of this water hammer. So before we discuss what is water hammer, how the effect of water hammer, is this a desirable, undesirable phenomena? And if it is undesirable, how we can protect the water supply system against this phenomena? First, we learn what is water hammer. So if the velocity of a liquid in a pipeline is abruptly decreased by a valve movement, we suddenly close the valve. Clear? So we reduce the velocity of liquid in pipeline. The phenomena encountered is called the water hammer. So when water is flowing in a pipe and you suddenly close the valve, as we have in our washrooms, clear, etc. Similarly, in water supply systems, when you suddenly close the valve, the velocity will be decreased abruptly. So as I said before, that when the velocity is reduced, where the effect will go? The pressure will increase. And then this pressure increase can be dangerous, because if it is beyond the desired limits, it can cause damage to the pipes. It can burst the pipes. It can cause vibration, noise in the pipes. So this phenomena is known as water hammer. This is very important problem in case of hydroelectric plants. In hydroelectric plants, what we have is that, let's say we have a dam, and from the dam we have tunnels, and these tunnels, they supply water to generate the hydropower. Clear? We store the dam water, and in here the water supply to, let's say, a turbine. So I write down here T, and then from the turbine the water goes to the downstream and it continue flow in the river. So this turbine is then connected to the generator and we are generating the electricity. Now what happens is that sometimes when the demand drops, now these pipes are huge tunnels. If you have visited dams, if you have ever visited the hydro power houses, clear, the water is coming through huge tunnels. This is very huge quantity of water. So if the demand on the turbine drops, we need to stop the water because this water is rotating the turbine and we are generating the electricity. So when you suddenly close the valve or any other arrangement here to stop the water, you can see very huge quantity of water will be suddenly brought to rest. Clear? So in hydropower, hydroelectric plants where the flow of water must be rapidly varied in proportion to the load changes on the turbine. So we have to suddenly close the valve because we want to stop the turbine. The load has dropped. We do not want to generate electricity for that period. So if you suddenly close the valve, this huge quantity of water you suddenly bring to rest. So what will happen? There will be enormous increase in pressure, and this increase in pressure, it can be dangerous. So this water hammer has burst large penstocks. Penstock is this pipe through which we supply water to the turbine. This is known as penstock. We will study turbines in detail. This is known as penstock. Originally penstock was name of a valve, but later on this whole pipe was then called penstock. So water hammer has burst large penstocks, causing great damage to hydraulic and power generating facilities in addition to loss of life and power generation. So that's why this water hammer, we have to reduce its damaging effect because it has burst large penstocks. So later on we will study how to avoid or reduce this. Clear? How to avoid it. If we cannot avoid it, how to keep the increase in pressure within limits so as to avoid the damage. So that's why later on I will tell you that what we do to avoid bursting of these pipes. But at the moment we say that this is the water hammer, and this water hammer, you can see that this is important problem in case of hydroelectric plants, and this water hammer has caused damage to the pipes, loss of life, power generation, etc. Now this water hammer, it occurs in liquid flow. This is in liquid flow pressure systems, whenever a valve is closed or opened fully or partially. So remember, in liquid pressure flow systems in pipes, this water hammer phenomena can occur whenever a valve is closed or opened fully or partially. Clear? So this terminology that we use, water hammer, so the name is given water hammer to this phenomena. This is perhaps misleading since this phenomena can occur with any fluid. So since we already see that water plenty available around us in the water supply systems, in the rivers, etc., you see commonly we have water. And in the water supply system that we supply to the community, etc., so commonly water we are using other as compared to other fluids or liquids. So that's why this phenomena was given the name as water hammer, because this water you suddenly bring to rest in a, it results in increase in pressure. So this was act like a hammer. Clear? Like a hammer effect. So this was known as water hammer, but it is written in your textbook that this is perhaps misleading because this same effect can occur with any liquid. Clear? So you can see this water hammer before we proceed. Now you can see the water hammer. Water is flowing in the plastic pipe. When we suddenly close the valve, you can see the effect. This is water hammer. This is water hammer. Water is flowing in an elastic pipe, and when we suddenly close the valve, you can see the effect. You can see the effect. This is water hammer, because in here you close the valve, you suddenly bring the water to rest. So we destroy the momentum, we destroy the kinetic energy. So as we already stated, that energy can neither be destroyed, neither created, so it be converted into another form. So this energy result into increase in pressure, and you can see the pipe, it has stretched. So if this water hammer pressure is more than the desired limits, it can burst the pipe. So it can be dangerous, it can burst the pipe, it can cause leakages at joints in the pipes. Clear? So that's why this phenomena is undesirable phenomena. And we have to keep these pressures that develop as a result of this water hammer. We close suddenly the valve within desired limits. If these are within desired limits, first we need to avoid it. If we cannot avoid it, we have to keep these increase in pressure within limits, means as low as possible, so that there is no damage to the piping system. So now we know that, yes.
सर ये जो पाइप की एक्सपेंशन हुई है सर, क्या हम कह सकते हैं ड्यू टू द accumulation of water?
This is not due to accumulation of water. This is due to the increase in pressure, because you suddenly destroy the kinetic energy of the water. So where the energy will go? This will result in increase in pressure. Clear? You cannot say that the quantity of water in the pipe has increased, because the water is flowing with the discharge. Q is equal to AV. So how can the discharge will be then more, as per your question? This is because that you see we have forms of energy. So the water is flowing with these forms of energy. It has the velocity head, it has the datum, and it has the pressure head. Now when you make this as 0, then between the two sections, Z is same horizontal pipe, so we ignore this. If you make this 0, where the energy will go? We already stated law of conservation of energy. Energy can neither be created nor destroyed. So now when you bring the liquid to 0, where this will go? It means that it will increase this pressure. This will increase. So due to this increase, the pressure expanded. So this is what we are saying, that this increase in pressure, it will be resisted by the fluid. That's why we consider compressibility of the fluid. And it will be also resisted by the stretching of the pipe walls in case the pipe is elastic. Now your question is clear?
Yes, sir. Thank you.
Okay. So now let us continue. Now we know that what is water hammer. This phenomena occur in liquid pressure flow systems, and it is undesirable. So now next we study that what is the physics of this water hammer, how this water hammer, as a result of this, the pressure increase occurs, and then how we can calculate this increase in pressure, because the pressure has increased due to water hammer. How we can calculate this increase in pressure, because for this pressure we have to design our water supply systems so that no damage can occur whenever this phenomena is encountered. So this is what we are going to study now in this coming topics. First we consider the instantaneous closure. Now this instantaneous closure means that what we see in this diagram here is that this is a reservoir, and from the reservoir, let me come here to this figure. This is a reservoir, and then from a reservoir the water flows in a pipe. This is the what we studied so far, and this water flows out from this pipe. This is what we consider the cases so far. When this happens, we have this normal pressure variation diagram. This is the pressure distribution diagram considering the friction in the pipe. When we consider the friction in the pipe, this is the sloping normal hydraulic grade line, because at every point it gives you P by gamma. This is P by gamma here. At any point, this is P by gamma, and so on. So this is the normal situation. Clear? Now the problem is that we have a valve. Clear? We have a valve here at end of this pipe, let's say at point N, and now we suddenly close the valve. This is the instantaneous case. This instantaneous case is actually physically not possible, but we consider this case to understand the real cases that we discuss after this. What this instantaneous closure means, that the time of closure Tc, this is denoted in your textbook, Tc is equal to 0, when it means that instantly you close the valve completely. This is what we mean by instantaneous closure. Time of closure Tc equal to 0. So why we say that it is physically not possible? Because whenever we close the valve, we take some time to close the valve. For example, in your washrooms, when you close the valve, you close it in 0.1 second, 0.01 second, 0.2 second, 0.3 second, 1 second. So that's why those are practical cases that we will discuss after this case, the real cases. But this case is physically not possible because we always take some time to close the valve. At 0, time is equal to 0, you close the valve. It is very difficult to do it. So this is what we mean by instantaneous closure. Clear? Okay. Now when you suddenly close the valve at Tc equal to 0, what will happen? Now you are destroying the kinetic energy of the fluid. So as I explained, what will happen? As a result of this, the pressure will increase. That's why you can see the pressure will move up from point P to R. This pressure will increase because we suddenly close the valve, you suddenly bring the fluid to rest. So this increase in pressure will occur from P to R. And as the pressure increases, because we compress the fluid here, we compress the fluid. So what happened? The fluid near the valve, it will be brought to rest. Then the next fluid particle will be brought to rest. Then the next fluid particle will be brought to rest. Then the next fluid particle will be brought to rest. Clear? This is like one is moving, second is moving, third is moving, fourth is moving. When it stops, when this stops, this is still moving. It will come here, it will stop. It will come here, it will stop. It will come here, it will stop. This is like, for example, a train is moving. So we have different, what we can say, compartments of this train. So when this suddenly moves, stops, you see that it will bring this to stop. It will bring this next compartment to stop. It will bring this next to stop. This is what can happen. For example, we are moving in a line. If the first person stops, then the other people following, they will also stop. So this increase in pressure, what will happen? That because the effect is transferring upstream, this will set up a pressure wave. So this pressure wave will travel with Cg. Now we consider Cj, we consider the pipe and the liquid both as elastic. So that's why Cj is written. Normally, the water was flowing with a velocity v when the valve is open. But now the effect is transferring because this is brought to rest. The effect is transferring up the pipe length. So how the effect is transferring? In the form of a pressure wave that is given by Cj. That's why we studied how to calculate this Cj, that with what velocity it will travel through the fluid. Now you understand why we studied the first topic. So this pressure wave, it will set up, it will travel with a velocity Cj, and as it passes at any point, it will bring that fluid to rest. What I say is that for this fluid, behind this Cj, what is the velocity? Velocity is 0. When the velocity is 0, that's why you see that this pressure is, increase in pressure is traveling with this pressure wave upstream. You can see here, as the pressure wave travels, it is bringing this increase in pressure all the way to the pipe inlet, or we can say to the reservoir. So when this pressure wave, when it reaches here, it will bring this pressure to this value. When this reaches here, it will bring this normal hydraulic grade line here to this. And the pressure is delta P by gamma. This is the increase in pressure due to this water hammer. When this wave reaches here at this point, it will bring this pressure to this maximum value. When it reaches here, it will bring this pressure to this maximum value. When it reaches here, it will bring this value to the maximum pressure from the normal pressure. And when it reaches here, so it will bring this pressure here to this maximum. So when this pressure wave, when it starts here, it causes this increase in pressure, and when it travels up the pipe, it brings all the pressure to the increased value. So now when the pressure wave reaches here at this point M, inlet to the pipe, when it reaches this point here, you see the hydraulic grade line, this will be this one here. It will be this line for whole of the pipe. Instead of this line, now the pressure variation line is this one. And why this increase in pressure occur? Because of the water hammer. Clear? So this water hammer has caused all the points in the pipe to experience this increase in pressure. And what is this increase in pressure? Delta P by gamma. So later on we will calculate what is delta P by gamma. Clear? How much increase in pressure will occur as a result of water hammer? This we can calculate. We will develop another equation for this to calculate. But at the moment, just I try to explain the physics of this water hammer, that as you suddenly close the valve, this is for instantaneous closure. It means that at time t is equal to 0, we close the valve. The pressure increases at the valve, and then that increase in pressure travel upstream all the way to the reservoir. How? Due to this pressure wave. Due to this pressure wave that setups, it travels, and as this pressure wave travels all the way to here, it will bring this increase in pressure for all the points in the pipe. Clear? Now the next thing to understand is that now when you close the valve, the pressure wave setups, and this pressure wave, it travels from valve towards the reservoir. How much time it takes to reach to the reservoir? So this we can calculate from S is equal to Vt. We have S is equal to Vt. So now S is what? S is your L, this L. And what is V? V is the velocity of the pressure wave, because this is the effect bringing. So that is equal to C with a subscript J. Why we see Cj? Because we are now considering pipe and the fluid both as elastic. And time is your T. Clear? So now from here, what we can write down, that T is equal to L divided by Cj. It means this much time is taken by the wave to reach from point N to point M. And if this wave is going to return, back to the valve, then how much time will take? This is the round trip. This is denoted by TR in your textbook, the round trip. It means the pressure wave generated here, it goes to the reservoir and then comes back. So it will be 2 times of this. So this will be equal to 2 times of that time, clear? So this will be equal to 2 into L divided by Cj. So the round trip for the pressure wave, this is 2L by Cj, because 2 times from N to M and then back. So this is the round trip, clear? Now this is here. The time for a round trip of a pressure wave from N is where? N is at the valve, to M, the inlet point, or to the reservoir, and then back again is TR is equal to 2L by Cj, where L is the length of the pipe. Now, in case of L, the round trip is 2L by Cj. Clear? The round trip is 2L by Cj. If we consider any point which is less than L, let's say I consider this distance x, then we say that when the pressure wave starts at B, then it goes here to the reservoir, how much time it will take? So now the distance is x. So for this, the time will be equal to x. This is what? L by Cj. So for that x distance, this will be equal to x by Cj. And if we say that when the wave coming here and then it try to come back to point B, what is TR? What is the round trip for this wave? So for this case, the TR will be 2 times of that. So that will be equal to 2x divided by Cj. Similarly, if we consider x naught, then it will be 2x naught by Cj. So it means that when the time round trip, this round trip, the wave starts from here and then comes back here. But as we move upstream, this time is reducing because the wave take time from here and then come back will be less for the valve as compared to the valve. If you consider any point here, so the wave take this much time to come back. This is TR for this distance, let's say x naught. So this time reduces, clear? So that's why at any distance x from inlet, then the time is 2x by Cj. For any distance L, it is 2L by Cj. But if we consider any distance x, such as point B, then it will be 2x by Cj. What will be for E? It will be 2x naught by Cj, and so on. So now, so far we say about this case, instantaneous closure, when you close the valve at time t is equal to 0, and the round trip for the pressure wave will set up because the pressure will increase, and then this pressure will travel up the pipe, and then this pressure wave can come back. I will explain why it can come back. So it will travel upstream, and as this pressure wave travel upstream, it increases the pressure in the pipe at all the points, all the way to the reservoir. You can see here, in this case, so in this case, you see for instantaneous closure, the increase in pressure, it is experienced by all the points in the pipe. You see the line all the way to the reservoir. So it means that when we suddenly close the valve at time t is equal to 0, when we suddenly close the valve, every point in the pipe flow will experience that increase in pressure. Now, how we can calculate it, this we discuss later. How much increase will occur due to the water hammer, this we derive the formula later. But at the moment, the thing to understand is that this increase in pressure, it will be experienced by all the points in the pipe. That's why it is denoted by this line here. You see, this is the transient hydraulic grade line. So this is one thing, that in case of instantaneous closure, all the points in the pipeline will experience that increase in pressure, whatever we will calculate later. Now the next thing to understand is that this increase in pressure which occurs at any point, for example, this increase occurred at B here, this occur at E, you see here it occur at E, at any other point. Similarly at valve, this increase in pressure has occurred. So the next question is that for how much time this increase in pressure will remain there before it comes back to the normal. For how much time this increase in pressure will remain before it comes back to the normal, because we said that this increase in pressure, it will not remain constant, because this is momentarily will happen and then it will disappear as the time passes. So in order to understand this, first we try to explain the physical description, that how this increase in pressure has occurred. Clear? And I said that the pressure wave travels here up to here and then it comes back. So when it goes from here to here, it will increase the pressure, and when it comes back, it will again bring the pressure to the normal pressure. It will again bring the pressure to the normal pressure when it comes back. So when the pressure wave passes one time, it increases the pressure or can decrease the pressure for the other side. But when it comes back, it bring it to the normal pressure. So let me explain first that why it can bring it to the normal pressure, then I will explain that for how much time the pressure should remain there. For this we come to this simple figure. Now you can see here that the water is flowing in a pipe from a reservoir under the normal pressure. You see here the friction is neglected, so that's why the line is horizontal. That's why the line is horizontal. Here we consider the friction, so the line is sloping. So just for understanding, we ignore the friction. So now you see that the water is flowing. You see here the water is flowing in a pipe with a velocity V under a pressure P by gamma. Now that we suddenly close the valve, so we saw that the pressure here will increase. And then it will travel in the form of pressure wave, and as it travels, it will bring all these points to the higher pressure. So as this wave passes through the points, it will bring all the pressure to the high value. So this is what you see in this second diagram, that as this pressure wave setups, we suddenly close the valve, the increase in pressure occurs, and this pressure wave will travel with a velocity Cj or C, you can consider, treat the pipe as rigid, no problem. So it will travel with a pressure wave, and as this pressure wave travels from this valve, this is, let's say, N point in the previous diagram, and as it comes to this NM point, which is inlet of the pipe or to the reservoir. So on this side, the fluid is flowing with a velocity V. But as this wave passes, it is bringing the velocity to zero. And because of this velocity bringing to zero, that's why the increase in pressure occur along this pipe. So when this wave reaches here at this point, then this line will be here. The hydraulic grade line will be here. When it reaches here at this point here, so you see all the points in the pipe, they experience that increase in pressure delta P by gamma from the normal pressure. So what will be the total pressure? P by gamma plus delta P by gamma. This will be the total pressure because the normal pressure is here. So this is P by gamma. So as a result of water hammer, then what is the total pressure? This P by gamma plus delta P by gamma. Clear? So now when this pressure wave reaches here, you see the pressure in the whole of the pipe is now increased. What is happening at the reservoir? Now at the reservoir, the pressure is this much. This is due to the pressure. Clear? But now the pressure shown here is this much. So that's why the pressure at M cannot be this one. It is this one. See, under normal condition, what is the pressure here? This one. So it cannot be more than this. So that's why you see that a high pressure wave has reached to the reservoir, but there the pressure head cannot be more than this. So what will be the effect of this? We have high pressure here in the pipe now and low pressure in the reservoir. So it means that some of the fluid will flow back to the reservoir. What will be the effect of this? Some of the fluid, it will flow back to the reservoir. So that's why you see that a reverse velocity will establish. So when now the velocity is established, when the velocity is 0, you have the maximum pressure. Now the velocity is established, so it will bring, what will be the effect of this? It will bring this high pressure to the normal. Because now the velocity is established, so the pressure is now reduced to establish this velocity. When the velocity is 0, the pressure goes up. Now the velocity is established, so the pressure should come down. So now a negative velocity will establish, a reverse velocity will establish, and it will bring this pressure down. So now as a result of this, another pressure wave will set up and it will travel from this point to this towards the valve. This is what you see here. This pressure wave will set up and it will travel from this point towards the valve. And this is the unloading pressure wave, because when it passes, it establishes this velocity V in the pipe, but on this side the velocity is 0. As this pressure wave passes, the velocity will be in the reverse direction towards the reservoir, and it will bring all the points to the normal pressure. As it passes, it will bring all the points to the normal pressure. As it passes, it will bring all the points to the normal pressure, P by gamma. So when this pressure wave, when it reaches, clear, when it reaches this N, what will be the situation when it reaches this N? When this pressure wave, when it reaches this N, what will be the situation? The whole of the pressure will be normal. This will be the line. The whole of the pressure will be normal, but the velocity, it will be in this direction in the pipe. This will be the velocity in this pipe. So you can see that when the pressure wave traveled from N to M, it was a loading pressure wave. Why? Because it increased the pressure. But when the pressure wave come back, it is unloading pressure wave, because it is reducing the pressure to the normal. Clear? So when this happens, this velocity, when it reaches the pressure here, this, so the velocity is in this direction. Now when the velocity is in this direction, so it is reverse at the valve. Clear? It is reverse. So what will happen? That another pressure wave will set up and it will travel through the fluid. Clear? And this pressure wave, it will bring the pressure below the normal now, because of the other side now. It will bring the pressure to the negative zone now. Instead of positive, it will bring to the negative zone, because the velocity here is now reverse. So that's why this pressure wave will set up and as it travels, it will bring the pressure below the normal. Now this is negative, and as it passes, it will bring all these points to the normal, below the normal, sorry, below the normal. So as this pressure wave, it travels, it is bringing the velocity to 0, and the pressure will be below the normal in the whole of the pipe. The pressure will be below the normal in the whole of the pipe. Clear? When this wave, when it reaches here, at this point, now the pressure is below normal. But the pressure at here can be this much. So now we have high pressure in the reservoir and low pressure in the pipe. That's why another pressure wave will set up and it will travel towards the valve. So that's why you see that the fluid will flow now from the reservoir to the pipe, because you have high pressure here and low pressure in the pipe. So now this velocity, which was reversed, it is now again flowing in the normal direction. When this pressure wave reaches here, the hole is negative pressure, and what is the velocity? 0. Now that we have low pressure here, but the pressure at this point can be this one, so again the velocity will be established in the pipe in this direction. So when the velocity is established, this pressure wave will travel and it will bring all the negative points to the normal pressure now. As it travels, it will bring all the points to the normal. It will bring all the points to the normal. And when it reaches here, then it means the whole of the velocity is in this direction towards the valve and the pressure is normal. So this is essentially same condition as what happened in this first case. What is in first case? The pressure is normal. You can see here in the first case, the pressure is normal and the velocity is flowing in here. And now we come back to the original condition. So it means we completed one cycle. What is one cycle? You have the normal pressure. What is the one cycle? One cycle is you start from here, you increase the pressure. That increase in pressure travel here. Then in the next phase, what happens that this pressure loading, unloading wave bring this pressure to the normal. Then in the next case, you go below the negative with same magnitude. So it continues the negative pressure, but then it is brought to the normal and we are here. So this completes one cycle. You see, we start from the normal, then a loading and unloading for positive pressure, and then a loading and unloading for negative, and finally we come back to the original. So this completes one cycle. So for ideal case, this one cycle will continue. And this is what is shown here in this diagram here in your textbook, that the pressure increase, then it remains there for some time, then it decrease to the normal, then it goes to the negative, then it continues to be negative, and then it comes back to the normal. This completes one cycle. This complete one cycle. And if we have ideal case, then this cycle will continue. This will be the second cycle. Then this will be the third cycle, and so on. So before I explain this graph, let me just show you a video so that you can see this positive and negative, which I show here in a video for a real case. So you can understand that what I explain here. So you can see here that the water is flowing in the pipe from a reservoir, and when you suddenly close the valve, see the loading, the unloading, and then the negative, loading and the unloading. This completes one cycle. Loading, then unloading. positive, then loading negative, unloading negative. This completes one cycle. So this is what you saw here in the video. So we have the loading, we have the unloading, positive, then the loading, the unloading negative, and this completes one cycle. Now let us come to answer the question, what was the remaining question? Two questions are remaining. That for how much time this pressure will remain at that point, at any one point, for how much time? And then how we can calculate this maximum pressure, this will conclude this case. So now in this case, you can see that when the pressure wave starts here, it brings this pressure here to R. It brings this pressure to R, and as it passes, it brings all these points to the higher value and so on. So this completes the loading. When it comes back, then it brings this pressure to the normal. So it means that for how much time the increase in pressure remain at the valve? It means that it remains at the valve with this time, 2L by Cj, because at this time, the pressure wave take to come here and then come back and bring the pressure to the normal for positive and for the negative again. So that's why you see here in the graph that the pressure increases. This is at the valve, and horizontal axis is your time. For how much time the increase in pressure remain at the valve? 2L by Cj. Because in this 2L by Cj, the pressure wave comes back and then bring it to the normal. So it will bring it here to the normal. And then we have the negative cycle. So that delta P by gamma, this is the same for negative and positive pressure. If any point is closer than this to the reservoir, this time will be short. For example, for X, this time is short, 2X by Cj, because X is less than L. So that's why for a B point here, if I show you for a B point here, or for a B point, how much time it will take? This much time, and then come back to bring it to the normal. But the pressure wave starts here. When the pressure wave reaches here, the pressure goes up. So it means that for some time, the pressure will not be there. After this pressure wave reaches here, then the pressure goes up. And then it remains at the higher value. When the pressure wave returns here, bring it to the normal value. So that's why in the graph you see that initially there is no increase in pressure, because the pressure wave did not reach from the valve to this point B. So that's why it is here. And when the wave reaches, it increases the pressure. And this pressure then remains for 2X by Cj less than that. And then it is bring down, and then there is no pressure. And then for the negative portion and so on, this cycle continues. Now, if we consider a point M, so at point M, for how much the pressure increase occur? So the pressure wave reaches here, it goes up, and then the unloading pressure wave starts. So immediately it brings down. So that's why at point M, you see that this pressure wave when reaches here, then this goes up, and then immediately it comes down because the unloading pressure wave starts. So that's why the point which are closer to the reservoir, the maximum pressure which is given by delta P by gamma, this will be remain there for short time. And as the point is further, for example, the valve, the maximum pressure will remain there for longer period of time. So now this is clear. Now let me quickly derive the formula for how to calculate this, then I will take a break. Because this should not take a time. I already explained. So this should not take a time before I take a break. So in this case, what we do is that we can calculate the pressure change by water hammer we consider a valve is closed abruptly but not necessarily completely. That's why when you close partially the valve, still the fluid is flowing with a velocity v2 less than v. If you completely close the valve, v2 will be 0. So as a result of that, you see the stretching of the pipe wall occur. That's why we have Cj. The joint or combined celerity of pressure waves, and then this pressure wave will travel up and it will increase that increase in pressure that we saw in the diagram. Clear? So a pressure wave travels up the pipe with a velocity Cj. So in short time dt, element of the liquid of length Cj dt is decelerated because it is reducing the velocity. Clear? Therefore, the mass m decelerated is the same as m is equal to rho into volume. This is what we discussed earlier. We apply the Newton's second law, and when we consider the forces here, P times A, P plus dP into A, where A is the cross-sectional area of this pipe, change in velocity is v2 minus v1. Why? Because this v1 is the initial velocity. The fluid is flowing with a velocity v. If the valve is completely closed, v2 will be 0. This will be 0 if completely closed. But if not completely closed, partially closed, then we have v2. So if we treat this v2 minus v1, we consider v1, let's say v, because the fluid is flowing with a velocity v. So using this formula here, Newton's second law, and simplify, for delta P is given by this equation. So the increase in pressure due to water hammer you can calculate from this formula. It can be partial closure or complete closure. When we have complete closure, then V2 is 0. And this is the formula that you can use for complete closure, rho Cj into V. Clear? And we can eliminate Cj in this equation. So this is the increase in pressure when we consider the fluid and the pipe as elastic. This is the increase in pressure we can calculate that will occur due to water hammer. And then the total pressure will be what? It will be P plus delta P. This delta P is just due to only the water hammer. But we have a normal pressure that occur in the pipe before the closure. So the total pressure will be then P plus delta P. If we have complete closure, as I said, this V2 will be 0. And then this formula reduces to this. As V2 is 0, this reduces to this equation. So now we studied about the instantaneous closure. In the instantaneous closure, we saw that all the pipe portion will experience increase in pressure, all the pipe points. And that increase in pressure, it will move in the form of pressure waves, and it will complete cycle between plus and minus pressures. Clear? And we studied that the further the point is located from the reservoir, more time the pressure will stay there. See, more time. And if the point is closer to the reservoir, the lesser time the pressure increase will remain there. But it is the same. This is also delta P by gamma. This is also delta P by gamma. But it will remain for shorter and shorter time as we consider points near the reservoir. And then we discuss how to calculate this delta P by gamma increase in pressure. So we develop the formula.